Next, we're going to look at derivatives of our sine and cosine graphs. So here is our graph of sine. And on this program, I have picked random points. Well, not random points, but a point on the graph of sine. I can drag it along there. And every time I have that point, the tangent is drawn. So the derivative would be the slope of that tangent line. Now, if I wanted to use the sine graph to graph the derivative graph, I would have to plot a point, find the tangent line, figure out the slope, and right now, you see there's a dot labeled derivative. The derivative is 1. Can you see that if I went to the top of pi over 2, then my tangent line would be completely flat. It would have a slope of 0, so I would have a point at pi over 2. So I'm going to drag this point up to the pi over 2, and we're going to see what happens. We know that this one should be 0, and this one is 1. We're just going to see what happens in between as I drag it. So as I drag it up a little bit, do you see that my tangent line is going down a little bit? So its slope is getting less steep. Makes sense that the derivative is coming down. And as I get close to here, where it's flat, perfect, it hits 0. Now, as I go to 3 pi over 2, do you see at 3 pi over 2 it would be flat again, it would be 0. Can you see in between pi over 2 and 3 pi over 2 that any tangent I draw would have a negative slope? So those slopes are now below. So we do this and we keep going, and it's like, wow, does it make a nice looking curve? That's kind of cool. What is the blue one? Right? If the regular one was sine, the derivative is cosine. So again, crazy, like, oops, wrong one. Crazy things happen in calculus. You want to find all the derivatives of sine, and they come up to be derivatives of cosine. And if we think, like, just to remind yourself of how far we've come, if we did the limit as h goes to 0 of sine of x plus h minus sine of x over h, and we would have to see if we could do this derivative and do this limit. It's like, it looks complicated. How would I get the h to cancel out? Looks like my mic is slowly dying. All right, do a switch. I ordered new batteries, but now they're not even lasting a period, so this is okay. And if we look at the graph of cos of x, it also gets that nice curve to it, matches up perfectly. Except instead of being a sine graph, since it goes down right at the beginning, it's going to be a negative sine graph. Now I'm going to tell you that these can be ones that are easy to mess up, because the derivative of sine is cos, but the derivative of cos is negative sine, and it's going to be easy to mix up that negative. What I recommend is you think about what a derivative means and the cos graph. If I think of my cos graph and I move a tangent line just a little bit to the right, can you see that its slopes are already negative? That, for me, is a good way to remember that the derivative of cos is negative sine. But if I think about my sine graph, and I think about starting here, my tangents are all having positive slopes to begin with. So if I imagine my sine graph, I imagine drawing a tangent line, and I see that positive slope. For me, that helps me remember that the derivative of sine is positive cos, and the derivative of cos, because those tangents are going to go negative right away, is negative sine. And this is the first time we're learning a new derivative rule since we did our power rule. Like, we did our power rule, and then we did special rules like product rule, quotient rule, and chain rule, all with just regular polynomials. Now we add these two, and we can mix them into our other rules. So what does that look like? I could find the derivative of sine to the 4x. This is a chain rule. And sometimes, you know how sine, you probably remember from sine squared, you wrote the 2 in between the sine and the x? This means the same thing, and some students actually like to write it this way, because for them it's easier to see the chain rule. It's easier to see that the sine x is inside of the 4. So for our chain rule, it's really important that we recognize what's the outside function, what's the inside function. In this case, the 4, the power of 4 is the outside function, and sine of x is inside of that. So if we were doing a chain rule says, do your derivative of your outside function and keep your inside function the same, multiplied by the derivative of the inside function, and so now the derivative of sine is positive cos. In the back of your book, then, it would be written like this. Right? They put that 3 back into its spot. Okay? But I don't mind if you wanted to write it in brackets there and have the 3 on the outside. Visually and mentally, it's a lot easier. Having that exponent in a weird spot makes it a little bit harder to see that it's the outside function and the sine x is the inside function. Here, we do have a function inside of another function. We notice that the 3x cubed is inside of cos. How do we know we need to do a chain rule? Whenever the inside function has its own derivative, you have to do a chain rule. So now my outside function is cos. The derivative of cos is sine. Negative sine. Right? Because cos goes down right away. So the derivative of cos is negative sine. I would keep the inside the same and then multiply by the derivative of my inside function. Okay. I want you to try the next 5 on your own. I'll put up the answers in a bit. So the y is not by itself in this one. We have the y inside of sine, so we have implicit differentiation. We would take the derivative of this whole thing on the left-hand side. We see that y is inside of sine. Sine is our outside function. So the derivative of sine is cos. Keep the inside the same. multiply by the derivative of the inside, dy dx. Easy. On the right-hand side, we have a product rule. Keep the first one the same, times the derivative of the second one, plus keep the second one the same, times the derivative of the first one. We want to get dy dx by itself. There's only one term with the dy dx. I just divide both sides by cos of y. Oh, I can check how you did on the next one. First of all, notice that you would have a product rule. And then simplifying this product rule, it becomes cos squared minus sine squared. And from grade 12 through calculus, we have a formula, which is up on the board over here as well. And cos squared minus sine squared was one of the identities you learned in grade 12 pre-calculus, or will learn, and it's equal to cos 2x. It is a chain rule. So outside function is cos, inside is the 4x cubed plus 1. Derivative of cos, negative sine. Keep the inside the same, then multiply by the derivative of the inside function. And I would leave it like this. I mean, you could do more, but I did leave it like that. I thought maybe I put the 12 in front. Whew. Quotient rule, chain rule. Which one do you keep the same in the quotient rule first? Top or bottom? Bottom. Yes. 100%. Don't need to do any more, right? All right, let's see how I did. Keep the bottom the same. Multiply by the derivative of the top. And in the derivative of the top, we have a chain rule, because there's a 3x inside of cos. So we do the derivative of the outside function, keep the inside the same, and then multiply by the derivative of the inside. Quotient rule continued. Then we subtract. Now we keep the top the same and do the derivative of the bottom. The bottom is another chain rule. Outside function is sine, and we have an x to the negative a half inside. Derivative of sine is cos. Keep the inside the same, then multiply by the derivative of the inside function. Last part of the quotient rule is keep the bottom the same, but square it. Okay, you might be tempted to put this squared and this exponent together, but you cannot, because this negative a half inside is just to the x, and the squared on the outside is to the whole thing. Okay? But this is where mathematics is going to tempt you to try to do things that you're not allowed to do. No, wait, we will end here.